So how do you choose the best set of predictors and build a model? What constitutes the best regression model depends on the situation. Best models strive to have relatively few predictors to keep the model simple. Lots of times we refer to this as the parsimonious model. A relatively high R-squared, a relatively small value of the standard error of the regression, relatively small p-values for the F and T statistics, no cases with extraordinarily high leverage, no cases with extraordinarily large residuals, and studentized residuals that appear to be nearly normal. Predictors reliably measured and relatively unrelated. So why do we build regression models? There are two reasons. One is to try to understand the relationship among the variables. In this case, we want simple models with unrelated predictors, and we want large t statistics, small p-values. Or we use the model to predict response variable values when given predictor variable values. In this case, we want a large R-squared, and collinearity is less of a concern. That's related predictors. We're going to get to that in a minute. There are several automated systems for searching out the best models once a single criterion is selected for optimization, including best subsets and stepwise regression. These methods don't check the assumptions and conditions and are vulnerable to other complications. And even though the process is automated, you can usually just dial it up in a computer statistical software package, human oversight and analysis is still necessary to guard against misleading results. Best subsets regression is based on choosing a single criterion of what you consider to be best. For example, you could consider the best model to be the one with the highest R-squared. You choose a modest set of potential predictors, and then a computer searches all possible models and reports the best 2-predictor model, 3-predictor model, 4-predictor model, and so on. This technique becomes increasingly impracticable as the size of the data set increases. Stepwise regression is another alternative. The regression builds the model stepwise from a given initial model. At each step, a predictor is either added to or removed from the model. The predictor chosen to add is the one whose addition increases the R-squared adjusted the most. The predictor chosen to remove is the one whose removal reduces the adjusted R-squared the least. For large data sets, checking the data for accuracy, missing values, consistency, and reasonableness can be a major part of the effort. Best subsets regression and stepwise regression do not check the assumptions and conditions, so human interaction must always be introduced to the process. Excel doesn't do anything even close to building models to either of these methods that we've outlined or any other method. So we're just going to teach you what those are this semester. If you want help learning how to do this in another software package, I'd be happy to help you. But for this semester, we just want you to know what they are. So now we're going to talk about a potential issue that comes up in multiple regression called collinearity. Predictor variables exhibit collinearity when one of the predictors can be predicted well from the others. Consequences of collinearity are that the coefficients in a multiple regression model can be surprising, taking on an unanticipated sign or being unexpectedly large or small. And the stronger the correlation between the coefficients, the more the variance of their coefficients increases when both are included in the model. And this is called variance inflation. This can lead to a smaller t-statistic and correspondingly large p-value. So recall the housing price data set that we started our multiple regression lecture with. And consider the two variables living area and bedrooms. A simple linear regression with just living area predicting house prices predicts about an $88.30 increase in mean price for each additional square foot of space. So that's the coefficient for living area, you'll recall, and we interpret that as a slope. And if we do a simple linear regression on bedrooms, it predicts $48,218.91 increase in mean price for each additional bedroom. Now suppose that we build a multiple regression model including living area and bedrooms. And we did this example earlier, but we weren't discussing collinearity then. If you recall, I said these are related and we're going to visit it later. Well, here it is now. So we do the multiple regression again using living area and bedrooms as a predictor. And we have the same regression that we started this whole topic out with. The coefficient for living area is positive 93.84, and for bedrooms is negative $7,483.10. So since the coefficient on bedrooms seems counterintuitive, meaning as you increase number of bedrooms by 1, we expect sales price to decrease by $7,483.10 after accounting for living area, seems counterintuitive. It turns out that the correlation between the two predictors, living area and bedrooms, is 0.66. So these predictors that are trying to predict house price actually predict each other pretty well. So meaning some of the information about bedrooms is included in living area and vice versa. Notice what happened to the standard error for living area. It increased from 2.33 to 3.11. Let's take a look at another example. Now look at living area versus living area and bathrooms. So we're going to look at living area versus housing price. And the simple linear regression predicts $88.30 increase in mean price for each additional square foot of space. And then if we use bathrooms as our single predictor, it predicts $77,084.36 increase in mean price for each additional bathroom. Now, if we include both living area and bathrooms in our regression, we still have positive values for our coefficients. But the standard errors have undergone significant percentage change from the simple regression to multiple regression model. For living area, the standard error went from 2.33 to 3.36, and for bathrooms, it went from 2778 to 3422. Turns out the correlation between these two variables is 0.73. So, when one of the predictor variables in a multiple regression can be predicted well from another predictor variable or a combination of other predictor variables, they are said to be collinear. We refer to this issue as collinearity or multicollinearity. People use both of those terms interchangeably. High collinearity leads to the coefficient being poorly estimated and having a large standard error and correspondingly low t-statistic and high p-value. And when this happens, the coefficient may seem to be the wrong size or even the wrong sign, as we saw in our first example with the number of bedrooms and living area in the model. The statistic that we're going to use to measure the degree of collinearity is called the Variance Inflation Factor, or VIF. So if you're measuring the degree of collinearity for the ith predictor, the VIF is 1 divided by 1 minus the r squared for the regression where you predict the variable of interest, your predictor of interest, that is, your x that is of interest, from all the other x's in the model. Notice that your y, the thing you're actually trying to predict with your regression, is nowhere in this variance inflation factor calculation. So you literally take your variable, your x variable, your predictor variable that's in question, use it as your y, rerun a regression with all the other predictors predicting it, get the r squared from that, and plug it into the formula. A common cutoff for VIF is greater than or equal to 4 to suspect collinearity, but some recommend a more lenient cutoff of 5 or 10. So as you can see, there's no hard and fast rule for determining the collinearity. Standard statistical software packages will report the VIF for each predictor when asked, but of course Excel is not a statistical software program. So to calculate the VIF for a predictor xi in Excel, you're going to run the regression of xi against all the other predictors, find the r squared sub I, that is the r squared for the regression that we explained in step 1, calculate VIF sub I equals 1 over 1 minus the r squared from that resulting regression in step 1, and you have your VIF. And of course, you'd want to do this for all the variables, all the predictors in your model, but that's just the calculation for one of them at a time. So let's do an example with the coaster data, the roller coaster data. If I wanted to do a regression of speed, so predict speed from drop, length, and duration, I probably would want to calculate the variance inflation factors for each of those predictors. So let's practice how to do that in Excel for the predictor drop. So the first thing I have to do, because there's some missing data in the data set, you'll see that when you start to play around with it. Each missing value is denoted by an asterisk in the Excel spreadsheet, is I sorted the Excel spreadsheet so that there are no missing values for any of the 4 variables. Of course, that reduces our sample size, but this is what we have to do. So after I get it sorted so that I have a value in each cell for my variables of interest, then I'm going to do the regression of predicting drop from length and duration. Now remember, my target that I want to do, my target analysis, is to predict speed from drop, length, and duration. But just for the calculation of the VIF, I'm going to take each variable one at a time and predict it from the other predictor variables. So if I want to practice doing it for the drop variable, I'm going to run a regression and put drop as my y and length and duration as my x to find that the r-squared for that regression is 0.456399. And then I simply plug that into my variance inflation factor calculation, and I get positive 1.84. Now, since that's lower than any of the suggested cutoffs, 4, 5, or 10, so far we don't have evidence of collinearity. So what do you do with collinearity? Well, collinearity does not affect the fit of the model or the predictions using the model. So if you're using your model for prediction, it's not as much of a factor. But it does make choosing the best set of predictors more difficult and can also mask or change the interpretation of the effect of a predictor on the response, which we already discussed before. So if you want to simplify the model by removing some of the predictors, how do you decide which ones to take out? If they're related, you have several choices of which ones to take out. So the way that you choose is take out the variables or keep the variables in that are most reliably measured. Keep the ones that are least expensive to find. Keep the ones that are inherently important to the problem. Or create new variables by combining variables. So those are just some ideas on how to deal with collinearity.